Hello, I am presenting our work on occlusion-aware visual foresight for self-supervised robot learning. In this work, we build upon visual model predictive control by Finn et al. The idea of visual MPC is to make a robot acquire a model of the surrounding objects in a fully self-supervised way and then to use this model to plan actions. For example, we can then ask the robot to push a selected item to a particular location. We used a Sawyer robot to collect 50,000 video sequences where the arm is pushing various objects over the course of 1 week with almost zero human intervention. A video prediction model was then trained on this data. After that, the visual MPC is ready for use. A human can then click on the designated pixel on the object and select a goal location, and then 200 action sequences are sampled and fed into the prediction model, which predicts the future video along with the future positions of the designated pixel. The actions which bring the designated pixel the closest to the goal are then applied to the robot. This is repeated at every MPC step. On the left, we again indicated the designated pixel by the red square. Here on the top, we can see the predictions of the DNA model by Finn et al. For 5 different action sequences. On the bottom, we show the heat maps, so the probability distributions of the designated pixel over time. We will show later how we use these probability distributions to rate each actions by how likely they are to bring the object to the goal. For the predicted images, you can see that the background is being erased. And also, for this image, you can see that the arm moves in front of the object, but still the model predicts that the designated pixel is moving, which is wrong. And we will present later an architecture which solves this problem. We will quickly recap the video prediction model by Finn et al. At every time step, the video prediction model P takes in the current image at step T0, for example, and the action A0, and predicts the next image by transforming the previous image. Also, it applies the same transformation to the distribution of the pixels. At the first time step, the pixel distribution has a 1 at the location of the designated pixel and 0 elsewhere. Later on, the model will transform this pixel, and of course there's uncertainty, so the distribution will flatten out and get a little bit blurry. In order to rate the actions, a cost function is computed from the predicted probability distribution of the designated pixel pt. In the work by Finn et al., this was simply the negative log likelihood of the distribution evaluated at the goal position g. However, the problem with this is that the probability distribution is often 0 at the goal position, and this cost also does not account for the proximity of the probability mass to the goal. We will show in a quantitative analysis later that this cost function performs poorly. We found a simple alternative which accounts for the distance of the probability mass to the goal. We compute the expected distance to the goal by pointwise multiplying the probability pt with the distance field to the goal point. Here's the goal point. The cost function is smoother and more informative about the proximity to the goal. In the quantitative comparison later, we will see that this cost function has a great advantage. For this task of pushing the blue box to the green dot, we used the model by Finn et al., together with the expected distance cost. Here we can see the predictions of the video prediction model for the best action out of 200 sampled action, and here's the corresponding moving probability distribution. We found that clutter does not hinder performance. We extended the action space beyond the capability of Finn et al.'s model by adding the ability to go on 2 discrete heights, one for pushing the object and one for moving over the object. This representation is better than having a continuous z-axis, since the model does not need to learn about all intermediate heights. We found that our algorithm was able to jointly optimize the continuous movement in the plane and the discrete movement in z direction. We set up a benchmark of 20 long-distance pushing tasks using 3 objects not seen during training and 1 seen object. The objects were placed precisely at the same initial locations in each trial. To evaluate performance, we measured the distance between the designated pixel after pushing and the goal pixel. The lower the better. The measurements were done by clicking on the respective locations in the image. This was carried out by a person unaffiliated with the research team. The bar graph shows the average distances and standard deviations for seen objects green and unseen objects blue. Random actions result in the biggest differences. These are the distances we get by the model by Finn et al. Using the cost which evaluates the probability at the goal pixel. We can see that it is only slightly better than random. On the right, we can see the score obtained when using the proposed expected distance cost, giving a significant performance gain. This task requires the robot to move around the can of Spam in order to push the cup to the left. When executing Visual MPC on this task, the arm collides with the obstacle and the task fails. To avoid this problem, the model needs to find a way around the obstacle. We try to solve this problem by defining a second cost to avoid pushing the can of Spam away from its original position, thus forcing the planner to move around it. For this purpose, we have a second designated pixel, the green dot, where the goal position is exactly its initial position. Both objectives are summed together and jointly optimized by Visual MPC. However, when trying to use the DNA model by finitl, we can see that the model fails to find a solution and the arm goes on a random walk. This is because the DNA model is unable to predict correctly what happens with the designated pixel on the can of Spam when the arm occludes it. In this work, we propose a novel occlusion-aware video prediction model named Occlusion-Aware DNA, or OADNA. In this model, we add the ability to copy pixels from the first frame of the sequence at t0. These skip connections here. With these skip connections, our model is able to recover objects in the background which become occluded during the predictions, and it also does not move occluded designated pixels. Here we can see that the model that we propose in fact recovers the background, while the model by finitl erases the background. Also, our model does not move the designated pixel in the background, while the model by finitl does move the designated pixel. In this example, the robot successfully avoids the can of Spam in order to push the cup to the left. Here, the robot successfully moves around the power drill in order to push the stuffed animal. We perform a quantitative comparison between the OADNA model and the DNA model, which uses our expected distance cost function explained earlier. 8 different tasks which require the arm to occlude an obstacle during movement were defined with 2 novel and 2 scene objects. The average distances to the goal for the case of novel and scene objects are shown by the blue and green bars. We show that on average the OADNA model is able to bring the object much closer to the goal and is also leaving the obstacle closer to its original position. On the other hand, we observe that the DNA model by finitl mostly fails on the multi-objective task. The fact that for both models the distances for novel objects are slightly lower than for scene objects is most likely due to differences in the difficulty of the task. Next, we will show a couple of other complicated tasks with multiple objectives. These 2 objects need to be pushed apart from each other. In this task, the order of execution matters because first the power drill needs to be pushed down and then the stuffed animal needs to be pushed to the right. The OADNA model finds this correct order all by itself. Here is another task where OADNA needs to decide the order of the execution by itself. In this work, we have introduced a novel occlusion-aware video prediction model which is able to maintain the background during predictions. We have shown that the OADNA model vastly outperforms the DNA model on a multi-objective task which involves occlusions when the arm needs to move around the object. Thank you for watching.